Welcome guys, hope you're doing fine, and as you can see here are two questions from the IMO of 1988. IMO stands for International Mathematical Olympiad, and it is very prestigious because it has very hard questions, and only 6 to 8 people are selected from each country to solve this. And the sixth question over here, I believe, is the hardest question ever asked in an Olympiad, and apparently was sent to 6 of the greatest mathematicians of that time, and they were not able to solve it in even 6 hours, but they still decided to put it in the Olympiad. But we'll be dealing with the fifth question here. So ABC is a triangle right angled at A, and D is the foot of the altitude or perpendicular from A. The straight line joining the incenters of the triangles ABD and ACD intersects the sides AB and AC at the points K and L respectively. S and T denote the areas of the triangles ABC and AKL respectively. Show that S is greater than or equal to 2T. So you have to prove that ABC, the area of triangle ABC, is greater than or equal to 2 times the area of triangle AKL. So let's start with the diagram. So first we'll be drawing the diagram, and as you can notice here, I put the right angle at the top. Now there's a simple formula to find the in radius of a triangle, and using that we can use some coordinate geometry, which I like a lot, to find the coordinates of IB and IC, and then we can derive the equation of this line, see where it meets AB and AC using intersection of lines method, and then by finding these points we'll be using the area formula, finding the area of AKL, and then find the area of ABC, and then we can figure it out. So first we'll be writing some representations or some symbols here. So mod P represents the area of a non-degenerate triangle, or polygon P, although we'll be using it for triangles here. And BC is the base of ABC. We'll be doing this to make it easier. So the area of ABC can be written as half into AB into AC because they're perpendicular to each other, or half into AD into BC. They're also perpendicular to each other, and AD is equal to AB into AC by BC. You can derive that from this, and then you can just use Pythagorean theorem to get this. And then we'll be taking AB as A and AC as B because we don't want to write AB and AC everywhere we go. So then this is what we're going to be writing this like. Then we're going to be assigning coordinates. So A is 0, 80, obviously, because this is 0, so it'll be 80 above D. So it'll be 0, AB by root A squared plus B squared. And B is on the left side of D, so it'll be negative. So it'll be minus, using Pythagoras theorem, we can take BD as AB squared minus BD squared is equal to AD squared. So basically, AB squared minus AD squared will give you BD squared. And what we want is the square root of BD squared, which is basically BD. So that's what we did here. And then simplifying this, we get A squared minus A squared B squared by A squared plus B squared, because this is the value of AD squared. Then you get A squared by root A squared plus B squared. And then we do the same thing with DC. And then we get B squared by root A squared plus B squared. And then we denote the incenters as IB and IC. And then RB, as you can see here, is the radius, or the in radius of ABD, and RC is the in radius of ADC. So the formula to find the in radius is delta by S, where S is a semi-perimeter, which is basically half the sum of the sides, or half the perimeter, as it says. And the area is basically just multiplying BD into 80 and then dividing it by 2. But then we don't want a large sum in the denominator, so what do? We rationalize it. So this will turn out to be a sum of roots or square roots, and then we just multiply it into its conjugate, and then we get rational, not exactly rational, but simpler to use denominators like this one. Then we repeat that for IC, and then this is what we get. And then to find the equation of a line, we find its slope and then plug in a point on that line to find the constant. So suppose you have a line and then passes through a point. What does that mean? If you put in that point, you will get the value of technically 0, but if you use only the coefficients of x and y, like if you only take the part ax plus by and you ignore c, you just get minus c as the value of ax plus by. So that is how you derive the constant. So first we derive the slope, and then we put in a point which we know is on that, because we can put IB into that and then we get this value. It doesn't really need to be on the right hand side or the left hand side. It can be whatever or wherever you want it to be. And now we'll be finding the slope of AB to find its equation, which is pretty easy. You see here, AB is just taking the slope of, it's basically just 80 by BD. So you get B by A, and then we get BX minus AY plus A squared B by root A squared plus B squared is equal to 0. And then we do that the same thing to AC, and then we get AX plus BY is equal to AB squared by root A squared plus B squared. And then we'll denote these equations as 0, 1, and 2 respectively. Now a point lying on two lines satisfies both their equations, obviously. So solving the equations gives that point. That's how you can derive that point. So we'll be taking equation 0 and 1, and then that'll give us the intersection of AB and IBIC, which is K. So this gives us minus A squared B by root A squared plus B squared, comma AB root A squared plus B squared, minus B by A squared plus B squared. And then we apply the same thing to L. As you can see here, we take AX plus BY, which is the equation of AC, and AC intersects with IBIC at the point L, so we get the point L by solving these two equations. So I just multiply them by suitable coefficients, and then I add the equations so that the x terms cancel out, and then I get the value of y. That's basically what I did here also. And now, since we got the values of k and l, and we know the value of a already, like the coordinates of a, we can just use the formula. Now, the area of ABC is half AB, which is pretty obvious. The formula to find the area of a triangle is half mod determinant of x1, y1, x2, y2 plus determinant of x2, y2 plus x3, y3, and then determinant of x3, y3, x1, y1. Basically, in a determinant, you're supposed to multiply this into this and then subtract it like this, like y1 into x2 gets subtracted from x1 into y2 here. So the area of AKL is half mod determinant of this thing plus determinant of this thing plus determinant of this thing. I basically just put these points and then just get the value, and then I get these values at the end. And then as you can see here, this and this cancels out, this and this cancels out. So what I'm left with is this and this. So I can take a squared, b squared common, and then a squared plus b squared can be eliminated from the numerator and denominator. So it's not square anymore, it's just a squared plus b squared in the denominator. So that's how I get that. Now we derive the areas for S and T. Now we'll be using a common inequality, which is a minus b whole square is greater than or equal to 0. We're assuming that a and b are real numbers here, obviously. You won't have imaginary values for the sides of a triangle, so this is always greater than or equal to 0 because a square of any real number is always non-negative. So then I expand this like this: a squared plus b squared minus 2ab. That's the identity for a minus b whole square. And then I transpose 2ab. Well, it's greater than or equal to. Equality holds when a is equal to b, but if I divide both sides by a squared plus b squared, then I get this. And then multiplying by ab on both sides, I get half ab is equal to a squared b squared by root a squared plus b squared. And remember, this is 2t, and this is s. So we can prove that s is greater than or equal to 2t. So that's how you can use coordinate geometry to do really amazing proofs and questions. Hope you enjoyed this video. Do like and subscribe if you really enjoyed it. Thank you. Bye bye.